In this video we're going to start looking at a graphical approach to the Fourier transform. So we'll start off by looking at even and odd functions. Now we've touched on this before in a previous video, and we'll also cover it in more detail in a future video. But we'll take out of it what we need in order to get this description together. So let's imagine we had the sine wave here. So this is a sine function. The sine function is an odd function, because if I was to look at the value for the sine of a value x, it would be a positive value. If I went to the same point, only negative, we would get a negative value. So we would have the f of minus x would equal minus the f of x. So this is an odd function. Now if I was to integrate this function from minus infinity to plus infinity, then you could see that this area here would cancel out with this area here, the negative area. So the plus and minus would cancel, and the plus area here and the minus area here would cancel. So eventually all of the areas would cancel out and we would get an area of nothing. Okay, so it means that the integral of an odd function from minus infinity to plus infinity is 0. Now we've touched on that before in the previous videos, and that's going to be of use for us. Now if we were to look at the cosine function here. Now the cosine function is an even function, because if we will look at the value of f of t, we get a height here, and the value of f of minus t would give us the same value. So it would be symmetric around about the y-axis, and it would have mirror symmetry on the y-axis. Now if we were to integrate this function from plus infinity to minus infinity, you could see that the negative area in here would cancel with the positive area here, and again the negative area there would cancel with the positive, so on and so forth. But you would be left with an area at the centre here. So this area here would add up with this area here, so you would get a definite value. So the integral of an even function from minus infinity to infinity isn't 0, it is an actual value. Now another thing to note is that if we were to multiply an odd function by an even function, we would get an odd function. If we were to multiply an even function with an odd function, we would get an odd function. If we were to multiply even by even, it would give us an even, and an odd by odd, it would then give us even as well. Now we won't get through a proof of that here, but we will go through a proof of it whenever we look at the odd and even functions. So let's look at the Fourier transform, and we'll split it into its components, and we'll see what happens when we work out the Fourier transform of even and odd functions. So we'll do it just for the forward transform, for going from the time domain to the frequency domain, but the same things hold going from the frequency domain to the time domain. So the forward transform here is given by our integral from minus infinity to infinity of our f of t e to the minus I omega t by dt. Now we can split the e to the a minus I omega t into the cos omega t minus I sin omega t. We can then split these two up by multiplying out by the f of t, so we have one integral from minus infinity to infinity of the f of t cos omega t minus the integral from minus infinity to infinity of f of t times I sin omega t by dt. Now in this first section here, we can see that I put a little e there. So let's imagine that this function f of t is an even function. That would mean that the f of t would be even, the cos omega t would be even, the f of t here would be even, and the sin omega t here would be odd. So in this instance here, we'd be multiplying an even function with an even function, which would give us an even function. And when we integrate that even function from minus infinity to infinity, we get an actual value. Now as I mentioned before, if we were to multiply the even with an odd function, we get an odd function, and if we integrated that from plus to minus infinity, we would get an value of 0. So we would only be left with this one term. This term here disappears. So we'd be left with the integral from minus infinity to infinity of f of t times the cos omega t. Now similarly, if we were to look at a purely odd function, we'd have an odd times an even, an odd times an odd, and that would mean that in this instance here we would have an odd times an even, which would give us an odd term, and again that odd term would disappear because when we integrate it from minus infinity to infinity we'll get a value of 0. So all we'll be left with was this term here, Now if I said odd times odd would give us an even, so that means that we would have an integral from minus infinity to infinity of an even function, which would give us an actual value, which would be the integral from minus infinity to infinity of minus f of t I sine omega t by dt. Okay, so this is what happens whenever we're looking at purely odd functions and purely even functions. Of course, not all functions are purely odd and purely even. Most functions have got odd and even parts. So in that case, both of these values here would occur. Okay, and we'll be back to our normal Fourier transform, or using e to the minus I omega t. Now, in order to go through the graphical representation, we'll look at it purely in terms of the odd version and the even version. Okay, so let's say, for example, we had a Fourier, look at the Fourier transform of a purely even function of time, then we would be left with this little section here, which would be the integral from minus infinity to infinity by dt. So that would be the one step. Another step would be taking the function f of t and multiplying it by this other function here, cos of omega t. Similarly, if we were looking at an odd function, we would get the sine version. Now what we're going to see in the next page really goes to the heart of our graphical representation, because we're going to take the cos omega t and we're going to create a surface, because we've in effect just got a function with two independent variables. And if we set the independent variables at 90 degrees, so one of them would be an omega axis and one would be a t axis, and we would be looking at that function cos omega t. So let's have a little look at that in the next slide. So let's look at what we do whenever we're using a graphical approach to describe the Fourier transform. So I have here a function of time here, which is a simple square function, and that's time axis along here, and that's the function of time f of t here. And we have along this axis the I omega axis, so this is our function of frequency, and that's f of I omega. So this here is the Fourier transform of this function here. Or alternatively, you could say that this function here is the inverse transform of this function here. So what we're doing is we're going to be modulating this cos omega t surface with this function here. By modulate, I just mean multiplying it. So it would be, if it was a purely real even function, then it would be f of t times this surface. So this thing here would modulate the surface, and then we would integrate in this direction. So along the t-axis, so that's the integral from minus infinity to infinity over dt, and this would give us our function f of I omega. Now alternatively, we could use the inverse transform, and we could go from the frequency axis back to the time axis using the inverse transform. So let's go ahead and we'll have a look at this surface, and we'll also look at the sine omega t surface as well. So here we have the cos omega t surface. Frequency is along this axis here, and the time's along this axis. And you can get a copy of this M file in the resources section, so I suggest you download it and have a little play with it, and it gives you a good indication of what that surface looks like. So this is our sine omega t surface, and you can see that we have our time axis here, our frequency axis along here, and our amplitude up here. So again, I suggest that you download that M file. It's in the resources section. You have a little play about with it, and it gives you a good indication of what the sine omega t surface looks like. So this is the cos omega t surface here, and as we've seen it, we have our frequency along this axis here, we have our time along this axis here, and this here is simply our cos omega t. So you can see here that whenever our value of our omega equals 0, so this is omega axis here, when omega equals 0, we would just have this line along here, which would be a value of 1 because cos of 0 is 1. And again, if we were to make t equal to 0, which is at this point here, then our omega value would again be at 1. So you get this cross here in the centre, and as we move out in any direction, we just get a cos omega t function, and you can see it increasing as the frequency increasing and also increases as the time increases. So along this axis here is our time axis. So if, for example, we had a square function here, this square function would modulate this surface, that is, we would multiply this surface. So the sections out here we go to 0, sections out here we go to 0, and you're left with the centre part. And then we would integrate in the time along the time axis in this direction from minus infinity to infinity, and this would give us this sinc function here in the frequency domain. Similarly, we could work from the frequency domain back to the time domain, and this would be our inverse transform, but in that case this sinc function would then modulate this surface, and when we integrate, we would integrate along the frequency axis here, and it would go back and it would give us our function of time, which would be the square function. Now we're going to look at this and an example on the next video of the square function. We'll go through it in complete detail. Okay, so let's go ahead and we'll look at the sine omega t surface and see what that looks like. So here is the sine omega t surface. Again, the time along this axis, frequency along that axis, and again it looks very similar, but you can see that in effect this function here gives us our sine functions. Okay, now along this axis we have our time, so this would be a function of time. So we would then modulate that function there, modulate the surface, the sine omega t surface with that function, and then integrate along the time axis to give us our function of frequency. Or alternatively, the inverse transform, we would modulate this surface with the function of frequency and then integrate along the frequency axis in order to give us our function of time. So before we go on to the next video to look at the Fourier transform of a square function in real minute detail graphically, we'll go through the quick derivation of it mathematically. So here's the mathematical derivation. It's the analytic derivation of the Fourier transform of a square function. So we can say that f of I omega equals the integral from minus infinity to infinity of our function f of t e to the minus I omega t by dt. Now if we would take our function here as the square function, then it's got a value of 1 from minus top and 2 to top and 2, and you can see that this distance here is going to be our top and 2. So we've got the integral from minus top and 2 to top and 2 of our function, which is just 1 times e to the minus I omega t by dt. Whenever we integrate it, we get minus e to the minus I omega t upon I omega, and that's from top and 2 to minus top and 2. So that gives us this value here. Now if we were to then multiply that by top and 2 upon top and 2, then we get f of I omega equals tau sine omega top and 2 upon omega top and 2. So again, this is our sinc function, but it's different from the Fourier series version because we don't have a division by t naught, okay? Because remember, we multiply dividend by t naught in order to derive the Fourier transform. So graphically, the Fourier transform then is the sinc function here. We cross over points n 2 pi upon tau, and the height there is going to be a value of tau. So that's all there is for this video. The next video we'll go through the detailed derivation of this square function graphically. So thank you for listening and goodbye.